Okay, to start out segment C, or part C, here are the metric prefixes that are important to know. The book basically tells you all of them, and not all of them are used very commonly. So these are the ones that are important to know. On the large end, we have tera, which is symbolized by a capital T. And so basically, when you want to use an abbreviation for a metric unit, you just combine the abbreviation for the prefix and the abbreviation for the base unit. Basically, the base unit would be things like meters, liters, or grams. So if you wanted to say a teragram, then that would be written as capital T, lowercase g. Capital T means tera, lowercase g means gram. Terameter would be capital T, lowercase m. And teraliter would be capital T, capital L, because that's actually, the capital L is the abbreviation for liter. Now, tera means a trillion. And well, one area where you run across that fairly common is in computers, where you can have so many terabytes of memory. So that is the metric prefix tera. There's also giga. The gigabytes are you have so many gigabytes of memory in your hard drive. Well, giga has a symbol of capital G, and that means a billion, or 10 to the 9th power of something, of a unit. Mega is symbolized by a capital M, and that means a million units. You hear things like megawatts fairly often. A watt is a unit of electrical power, and it is a metric unit. You don't really need to know anything. Well, you don't even need to know that much. But anyway, when you talk about like the output of a power plant, they'll often give it in so many megawatts per hour, or that kind of thing, or megawatt hours rather. And so megawatts would be a million watts. And 2.5 megawatts would be 2.5 million watts. Kilo is 1,000. The symbol for that is a lowercase k, and that means 1,000 of something. That's pretty commonly encountered in things like kilometer, because a kilometer is about half a mile, so kilometers are used a lot in measuring relatively long distances. And kilometer would just be lowercase k, lowercase m. So that means kilometer. Kilogram is lowercase k, lowercase g. And that is the standard unit for mass in the SI subset of the metric system. And those are the prefixes of interest that give a unit a value greater than 1. And so that's why I drew this line here, because anything below the line is less than 1. Anything above the line is greater than 1. If you just want to say 1 of a unit, then you just give the base name of the unit. So 1, for instance, would be things like meters, or liters, or grams. And then below less than 1, the prefixes of interest, the ones that are important, would be deci, lowercase d, followed by the symbol for the base unit. And that means 1/10 of a unit. So a deciliter is 1/10 of a liter. Centi, which is 1/100th of a unit, and the symbol is lowercase c. So centimeter is lowercase c, lowercase m, and that's 1/100th of a meter. Or in other words, there are 100 centimeters in a meter. There's milli, which is the letter lowercase m for the symbol, and the value is 1/1000th of a unit. So for a milliliter is 1/1000th of a liter. Or in other words, there are 1,000 milliliters in 1 liter. The next one of any importance is micro, which stands for 1/1 millionth of a unit. Now we're getting down into units that are pretty small here, but in science, we keep improving things. We just can't help ourselves. And so we get to the point where we're able to measure smaller and smaller and smaller quantities. So measuring microgram quantities of a substance or measuring distances of a micrometer, that's actually not that difficult in the world of science these days. So we need a prefix for that kind of magnitude, and micro it is. Micro, of course, as we think of the word micro as generally meaning very small, and indeed it is very small, although not the smallest metric prefix. The symbol for that became a bit of a problem because they'd already used capital M for mega and lowercase m for milli. So now what? Well, what they did is they went and they raided Greek. And this symbol here that looks like a U with a tail on the front is actually the Greek letter mu. That's what they call it, mu, like a cow. And if you write it a little different like this, you can kind of see how that became an M when the Romans invaded and stole everything from the Greeks. So it is kind of a predecessor of our letter M. And when it's printed, it looks kind of like this. The uppercase capital mu is exactly like our capital M. The lowercase mu looks like this when it's printed. Again, it looks like a U with a tail on the front of it. And that means 1/1,000,000th of a unit. Then we have nano, which is a billionth of a unit. That's just a lowercase n. So a nanogram would be lowercase n, lowercase g, that's nanogram. And pico. Pico, as symbolized by a lowercase p, means 1/1,000,000th or 10 to the minus 12 of a unit. And there are units that go even below that, like atto, that's 1/quintillionth. Oh, sorry, atto, that's 1/quintillionth. But we're not going to be too concerned about anything below pico for our purposes. This is general chemistry, not advanced stuff. So those are the metric prefixes. There are converting from one unit to another within the metric system I mentioned is just a matter of essentially moving the decimal point around because everything is based on factors of 10. Converting between English and metric units can be kind of difficult because, well, for one thing, in the English system, most things are not based on factors of 10, and the metric system is. So you have to find a way to relate one unit to another. Like, for instance, if you want to convert from inches to centimeters. There is a very useful and extensive conversion factor sheet that comes from another book, not the one we're using, but a different book, which I have posted on D2L. And this gives conversion factors between English and metric, and also from one English unit to another for length and mass and volume and energy and speed. These are useful conversions here, because otherwise you have to convert, like if you have miles per hour and you want to know what that is in meters per second, which is the standard SI unit for speed, then if you can use these conversions here, because let's see, you have meters per second here and you have miles per hour there. So this many meters per second equals that many miles per hour. And that makes it much easier. Otherwise, you have to convert miles to meters and hours to seconds separately, and then put them together and get your final answer. And I will show you how to do that, but it's much easier if you just use these conversions here because they've already done the hard part for you. And we've also got force and pressure. We won't worry about those until later. Also on this conversion factor sheet that I posted, there is metric prefixes, the ones that we went over and others besides, some physical constants, some of which will be useful in chemistry, others of which are primarily physics, and the Greek alphabet if you want to learn how to read Greek. There it is. So that's on D2L up at the top. I moved it to the top because it's something we'll be able to use all semester. I will also allow you to use that conversion factor sheet on your tests, although I will actually I will print them out. I will print some out and give them to you with the test. Okay. The next thing in topics to come along would be density. We dealt with density somewhat in the lab experiment on Tuesday. And so you may recall that density is the amount of matter that's present in a certain volume of a substance or a sample of substance. So it's essentially mass of a sample or an object divided by its volume. And the units for density would be any unit of mass over any unit of volume. And so we'll get to the units in a moment. Just remember that density is a characteristic property of any pure substance. It's also a characteristic property of mixtures if you specify the proportions of things in the mixture, then it would have a characteristic density. For a pure substance, well, a pure substance only consists of one kind of atom or molecule, so you don't have to specify composition for a pure substance. So a pure substance will always have the same density. So copper will always have the same density no matter where it comes from. If it's, say, a copper penny from back when they actually were made of copper, or if it's a piece of copper pipe from the walls in your house, or copper wiring from the walls in your house, or a piece of copper ore from the ground, assuming that the copper is pure, then it should have the characteristic density of copper. And the nice thing about that is that not only do we know what the density of a substance should be ahead of time, but if we have an unknown substance, we can find its density and we can identify it, or at least narrow down what it might be by finding its density and comparing that density to the known density of various known substances. Okay, I like the way the old book covered this, so I'm going to switch to my old notes for a moment here. And in density, density is a derived quantity, so it's not something that you can measure directly. You measure the mass of the substance and the volume of the substance separately, and then mass divided by volume will be the density. It can have any units of mass or weight over volume, and that would qualify as a density. But the most common units would be grams per cubic centimeter for solids, grams per milliliter for liquids. And actually those two are the same thing, because remember, as I mentioned in lab, 1 cubic centimeter is the same as 1 milliliter. And so grams is a unit of mass, and cubic centimeters or milliliters would be units of volume, and they actually happen to be the same thing. And for gases, we usually use grams per liter, just because for gases are not very dense at all. So if you use a small volume like a milliliter, you're going to have a really small number for the density. Whereas if you use a larger volume like a liter, which is 1,000 milliliters, you end up with a more reasonable number for the density of a gas. But if we refer back to what we said about the SI system and what the standard units are for mass and volume, the standard SI unit for density would be kilograms per cubic meter. And that is a unit of mass over a unit of volume. So that is a density, and that is the standard SI unit. Although, like I said, in practice, you'll probably use one of these others. All right, can be used to identify substances. Densities are known for really just about any known substance. And density can be used as a conversion factor between mass and volume. So density is equal to mass over volume. And if, say, because densities are known for essentially every known substance out there, if you know what substance you're dealing with, you can look up its density. You don't really have to calculate it, unless calculating it is the whole point of the exercise, like in experiment 1. But normally you would just look up the density of the substance, and you could then use that to, say, find the volume if you know the mass, or find the mass if you know the volume. So algebraically rearranging this equation, density equals mass over volume, it's also true that volume equals mass over density. So if you know the density of the substance and you know its mass, just take mass divided by density and you'll get the volume. And we can do that because if you're looking for the, if you want to solve for the substance or the variable that's on the bottom of a fraction, you can just switch it with whatever is on the other side of the equation. So switch the d and the v, and we've got v equals m over d. And it's also true if we rearrange the equation again, if we want to find the mass, that would be volume times density. So if you know the density and you know the volume, you can find the mass. It helps with these three-term equations like density equals mass over volume to put the terms in a little triangle like I've drawn here. And you just have to be sure that you put everything in the right space. So density is mass over volume. What that means is mass goes in the top space on the triangle and density and volume go on the bottom. So you just have to remember that when you're setting up the triangle, you don't necessarily put what you're solving the equation for in the top space. Whatever goes on top of the ratio or the fraction goes on top of the triangle. So density is mass over volume. It's also true that volume equals mass over density. And it's also true that mass equals density times volume. So it's very handy to put it in a triangle like that because it makes rearranging the equation a lot easier. And so you don't have to basically spend a lot of time thinking it out. One of the standards that was used in setting up the metric system was water. They set it up so that the density of water would be 1 gram per milliliter or 1 gram per cubic centimeter. And that is the one density that you should remember. Any other density, if you need it, I would give it to you, or I'd give you a table where you could look it up. But water, because that is part of the basis of the entire metric system, you should remember that. 1 gram per cubic centimeter or 1 gram per milliliter, same thing. So an example of what you can do with density is, for example, if you have a piece of metal that has a mass of 100.0 grams and a volume of 12.72, ooh, I didn't know, milliliters, what is its density? And what metal is it? Okay, so you've given enough information to find the density. Density is mass divided by volume. The mass of this piece of metal is 100 grams, and the volume is 12.72 milliliters or cubic centimeters, same thing. And when you work that out, that gives us a density of 7.862 grams per cubic centimeter. And that matches the density for iron if you look it up in a table. And so it's almost certainly iron. Another example might be a 24 karat gold ring. So actually 24 karat, just to be technical about it, 24 karat gold actually isn't totally 100% pure gold. There's a little bit of silver in it just to make it hard enough to be usable. Pure 100% gold is so soft that you really can't do anything with it without deforming it. So even 24 karat gold has to have at least a little bit of silver in it. But we'll assume for the moment that 24 karat gold is close enough to being pure that we can use the textbook density for gold. So this pure gold ring has a mass of 29.8 grams. What would be its volume in cubic centimeters? Knowing that the density of gold is 19.3 grams per cubic centimeter. Well, we have from our equation over here, if we want volume, it's mass over density. So volume is mass divided by density. And mass divided by density is the same as mass times 1 over density. So we can take 29.8 grams divided by 19.3 grams per cubic centimeter. And the reason I wrote it like this, mass times 1 over density, is so you can see how the units work out. The density is 19.3 grams over cubic centimeters, but 1 over that, in other words, if you turn it upside down, that would be 1 cubic centimeter over 19.3 grams. And so that would be mass times 1 over density. The mass is 29.8 grams. 1 over the density is 1 cubic centimeter over 19.3 grams. Notice that we end up here with grams in the numerator and grams in the denominator, which means that the grams cancel, leaving you with units of cubic centimeters, which is a volume unit. And that's what you wanted. So by arranging the equations the right way and making sure that the units work out the way they should, you can help ensure that you're getting the right answer. And the answer in this case is 1.544041451, which is a ridiculous number of digits. So I cut that down to 1.54. There's a specific reason that I used that number of digits, but we haven't gotten to that yet. So don't worry about it yet. But that's the kind of thing that you're going to have to do with answers on mathematical questions in the future, is determine how many digits it should have based on the number of digits of the numbers that you put into finding it. Okay, so that's density. We come now to measurement uncertainty, the question of accuracy and precision. And we don't have a lot of time left on this lecture. So let me see. I'm going to come back to significant figures in our next lecture. For now, I'll just cover accuracy and precision. Whoops, accuracy and precision. Accuracy is when you're making a measurement or doing a calculation. Accuracy is how close your result is to the actual true value of the quantity you're trying to measure or calculate. Okay. A lot of times we don't know the true value of the quantity we're trying to calculate. If we're, for one thing, if we're measuring the mass of an object, we don't necessarily know what the mass of that object really is, unless it's, one of the weights that you put on a balance that has the mass stamped right on it. Otherwise, you probably don't know what the mass of the object is. If I tried to take the mass of this pencil, I don't know what that mass is supposed to be. So I can't really directly judge the accuracy of the number I get for the mass. What you can do to try to minimize error is take the mass of the object several times. The standard is usually at least 3 times. Write the numbers down and take their average. That is, if you do 3 trials, add up the 3 numbers and then divide by 3. And that will be your average number. And usually, a lot of times anyway, errors in individual measurements will cancel each other out if you do the measurement more than once and average the results together. So that improves your accuracy. And also, if you do the measurement more than once, it allows you to judge precision. Precision is related to accuracy, but it's not the same thing. Accuracy is how close your answers are to the true value, which you may or may not know. Precision is how close the individual answers are to each other when you do multiple trials for the same measurement or the same calculation. So if I weigh this pencil 3 times and look at those 3 numbers that I get and see how close they are to each other. If those 3 numbers are very close to each other, then I have really good precision. In fact, if I'm using an electronic balance, there's a pretty good chance that all 3 masses would be exactly the same, and that would be perfect precision. If the masses differ significantly, then that would be an example of poor precision. And the general rule of thumb is that if you get good precision when you do multiple measurements, then your accuracy is probably pretty good also. That's not always true, but it's true often enough that precision is worth looking at when you do multiple measurements. It's possible, though, for one to be good and the other to be bad. You know, good. It's possible to have good accuracy and poor precision. It's possible to have poor precision poor accuracy and good precision. And it's possible, it's possible for both to be good, and it's possible for both to be bad. The case is often illustrated with dartboards, the dartboard analogy, which I will draw here. Okay, so for a dartboard, say you're aiming for the bullseye, and you get darts that go, say, here, 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 and here. That would actually be an example of good accuracy and poor precision. Because notice how far apart those four darts are. They're all over the place. But if you take the average position of those 4 darts, it's right on the bullseye. And that doesn't happen very often in scientific endeavors, but it does happen once in a while. It is possible. It's also possible that you might have poor accuracy and good precision. So for example, if you're aiming for the bullseye and your 4 darts go like this, they're all sort of clustered up in one corner way far away from the bullseye. Well, that would be good precision because they're right near each other, but very poor accuracy. You're nowhere near the bullseye. What if they're both good? Well, good precision and good accuracy would look something like this, where the 4 arrows are clustered right around the bullseye, and the average position of them is right on the bullseye. And on the other hand, it's possible for both of them to be poor. So maybe one arrow goes here, and another goes here, and another goes here, and the other one goes there. So notice the average position of these arrows is not going to be anywhere near the bullseye. It's probably going to be right about where that one is. And they're not very close to each other either. So that would be an example where they're both poor. In calculations, in doing calculations, whenever you calculate percent error, you're calculating accuracy. So a small percent error means good accuracy. Large percent error means poor accuracy. When you're calculating precision, the quantity we usually calculate is called deviation or percent deviation. And so if you have a large deviation, that's poor precision. If you have a small deviation, then that's good precision. All right, and so next time, we will start with significant figures. Significant figures gets a little involved though, so I want to have time to devote to that. So that'll do it for today, and I will see you next time.